Welcome back to Physical Science 101. This is our first lesson and our final unit, Unit 7, which is nuclear physics. What we're going to discuss in this unit are the structure of nuclei and the reactions that nuclei undergo. We'll talk about radioactivity, and finally we'll talk about how we can get energy from nuclear reactions. Let's get started with the structure of atoms and their nuclei. This is a picture that we've seen before when we talked about electricity. This is a helium atom. You can tell that because it has 2 protons in the nucleus. It also has 2 neutrons in the nucleus. And then it has 2 electrons orbiting the nucleus. The electrons are bound to the nucleus through electric attraction. So the positive charges in the protons in the nucleus attract the electrons and exert a force which keeps them together in the atom. But the real question is, what is it that keeps the nucleus together? We have those 2 protons very close to each other in the nucleus, so we know that they repel each other by the electric force, but what is it that keeps them in the nucleus? There must be another force. That force is the nuclear force. And what we know about the nuclear force is that all nucleons being the protons and the neutrons, all nucleons attract each other very strongly at a distance of 10 to the minus 15 meters. So that is very, very small. That's 0.0 and a total of 14 zeros followed by a 1 meters. So that is a very, very, very tiny distance. That's in fact the size of the nucleus. So essentially, when we can get 2 protons to touch each other, they attract each other very strongly. And if we have a couple of protons and a couple of neutrons, that is strong enough to overcome the electric repulsion that the protons face, and that can hold them in the nucleus. So the situation we have is that when protons are far away, they repel each other. So it actually takes work to bring these 2 protons together. When the 2 protons are far apart, we have to exert a force over a distance to get them to approach each other, and that force that we have to apply gets stronger and stronger and stronger. The electric force gets stronger and stronger and stronger as those protons get closer to each other, until finally, when we get them within 10 to the minus 15 meters of each other, essentially when we get them touching, then they will be attracted by the nuclear force and actually stick together. So that is what we know about the nuclear force. All nucleons attract each other. Protons attract protons, neutrons attract neutrons, and neutrons attract protons when they are very close to each other, and very close being 10 to the minus 15 meters. So I have a couple of questions for you. The first is, protons and neutrons collectively are called A, particles, B, nucleons, C, heavy particles, or D, alpha particles. Please pause, think about it, and when you have an answer, hit play. The correct answer is B, nucleons. Protons and neutrons together are called nucleons. We give them that name because the protons and neutrons are found in the nucleus. Electrons are not nucleons because electrons are not found in the nucleus. They do not participate in the strong nuclear force. The electrons are bound to the nucleus by the electric force only. But protons and neutrons feel the strong nuclear force, which is why we find the protons and neutrons in the nucleus, and therefore we call protons and neutrons nucleons. One more question. The nuclear force is A, attractive when nucleons are closer than 10 to the minus 15 meters, B, repulsive when nucleons are closer than 10 to the minus 15 meters, C, attractive when nucleons are farther than 10 to the minus 15 meters, or D, repulsive when nucleons are farther than 10 to the minus 15 meters. Once again, please pause, think about it, and hit play when you're ready. The correct answer is that the nuclear force is A, attractive when nucleons are closer than 10 to the minus 15 meters. So that's what we know about the nuclear force. The nuclear force is an attractive force. Protons attract protons, neutrons attract neutrons, and protons attract neutrons, and vice versa, but only when they are very close to each other. And very close in this case is closer than 10 to the minus 15 meters. So the correct answer is A. The nuclear force is attractive when nucleons are closer than 10 to the minus 15 meters. Now, the result of the strong nuclear force is that a helium atom, which comprises 2 neutrons and 2 protons, actually weighs less than 2 neutrons and 2 protons. So if we were to have 2 neutrons and 2 protons separately and then bring them all together, then the resulting helium nucleus actually weighs less than the mass that we started with and the mass of the 4 particles separately. So when we combine those 4 particles, we actually wind up with less mass than we started with. The lost mass is given up as energy. This brings us to Einstein's equation of energy and mass equivalence, which is that mass energy is equal to mass times the speed of light squared, or E for energy is equal to m for mass times c for the speed of light squared. M in this case is the amount of lost mass, and so the mass energy that is lost when the 4 nucleons combine to make a helium nucleus is actually converted into kinetic energy and then into thermal energy. So this is the release of energy in fusion. We fuse the 2 protons and the 2 neutrons together into a helium. That reduces the mass of the product, and then that releases energy. That releases an amount of energy equal to the lost mass times the speed of light squared. This doesn't just happen for helium. The more nucleons we bring together to make a bigger nucleus, the more mass energy is given up to a point. This graph shows you the mass of a nucleon, so the mass of a proton or the mass of a neutron in a nucleus versus atomic number. Atomic number is 1 for hydrogen, 2 for helium, and so on. It is the number that's above the element in the periodic table. It also tells you the number of protons that are in a nucleus. And what you can see here is that the more nucleons we bring together to make elements of higher and higher atomic numbers, the mass of a nucleon decreases until we get to iron. So iron has the lowest mass per nucleon. After iron, as we increase, go further up the periodic table, all the way up to uranium, the mass of a nucleon actually increases, which means that we have to actually add energy to fuse elements together past iron. It also means that if we were to make a uranium, then we could actually release energy by splitting it up into lower atomic number elements. So here we have a uranium nucleus, and we break it up into lower atomic number elements, and we release energy that way. So the parts of the uranium actually weigh less than the uranium itself. So this process, where instead of bringing bringing nucleons together to make heavier nuclei. This splitting of nuclei is called fission. So we can release energy from the heaviest nuclei by splitting them and having them go the other way on that chart from uranium towards iron. So here's a question. When protons and neutrons join to make a nucleus, energy is released and A, mass is lost, B, mass is gained, C, the mass is constant, or D, temperature decreases. Please pause, think about that, and hit play when you're ready to go. The correct answer is that if we were to take free protons and free neutrons and bring them together to make a nucleus, then energy will be released. The form of energy that is released is mass energy. So mass is lost. So when we bring two neutrons and two protons together to make a helium atom, then the helium atom will actually have less mass. And it is the loss of the mass that gives us the energy that is released. That also tells us why a helium atom doesn't fall apart, because it doesn't have enough energy to. The helium atom cannot spontaneously fall apart into two protons and two neutrons because it doesn't have the energy to do that, because it has lost mass. So the correct answer is, when protons and neutrons join together to make a nucleus, energy is released and A, mass is lost. Now in this unit, we're going to be talking about elements and their isotopes. So that means whenever we talk about a nucleus, it will have both a name and a number. So for example, there is helium-4, which we can either write just that way, helium-4, or we can use the symbol for helium, He, with a superscript prefix. So a superscript 4 before the helium. So either helium-4 or He with a superscript prefix of 4. Now what does that mean? The 4 tells us the number of nucleons in that atom. So the total number of protons and neutrons. This is also called the mass number. So when I say helium-4, the 4 is the mass number. The He, or helium, tells us that there are 2 protons in that atom. How do we know that? Well, that's where we go to the periodic table. We go to the periodic table and we find He for helium, and we see that that has a number 2 above it. That number 2 is called the atomic number or the element number. So the atomic number and the element number in this case would be 2. The mass number would be 4. So what we learn from that is that because this is helium, which is atomic number or element number 2, that nucleus has 2 protons in it. How many neutrons does it have? Well, we take the number of nucleons of 4 and we subtract 2. So we know that there are 4 neutrons and protons and that there are 2 protons. So 4 neutrons and protons minus 2 protons leaves us with 2 neutrons. So this is the helium-4 isotope. There are other isotopes of helium. So for example, there could be helium-3. If there were helium-3, that would be 2 protons because it's helium and 1 neutron because 3 minus 2 leaves us with 1 neutron. So helium-3 would have 2 protons and 1 neutron. Let's do an exercise on that. I would like you to please give me the number of protons and the number of neutrons in the nucleus of each of the following isotopes: cobalt 60, potassium 40, neon 24, lead 208. So you will have to use the mass number, which is the 60, 40, 24, and 208, and the atomic number, which is what you will get from the periodic table, to figure out the number of protons and the number of neutrons in each of the following nuclei. So please pause and do that, and hit play again when you're ready. Okay, I'm going to make a table: cobalt 60, potassium, that is a K, 40, neon 24, and lead, that's PB, 208. Okay. So then we'll start with the number of protons, and we get that from the periodic table. For cobalt, that number is 27. For potassium, that number is 19. For neon, that number is 10. And for lead, that number is 82. Okay, so the number of protons we get right from the periodic table by looking at the number that is above the element. Now for the number of neutrons, well, this number right here is the mass number, which is the total number of nucleons. We just have to subtract the element number, the atomic number, from the mass number to get the number of neutrons. So 60 minus 27 leaves us with 33 neutrons. 40 minus 19 leaves us with 21 neutrons. 24 neutrons and protons minus 10 protons leaves us with 14 neutrons, and 208 neutrons and protons minus 82 protons leaves us with 126 neutrons. Next time we're going to come back and we're going to talk about the reactions that nuclei can undergo. Basically how a nucleus of one element can become a nucleus of a different element. Until then, think science.